In this lecture, we will see some of the examples of undirected graphical models or Markov random fields. The first one is Ising model. In Ising model, we are looking on a two-dimension or three-dimension. We are basically trying to mimic the behavior of magnets. So the variable here are binary variables, which represents maybe positive or one or negative one. So you can think of this as spin up or spin down of the atom. Which so when neighboring spins are in the same directions, they are called ferromagnets. When they try to align in opposite directions, then they are called antiferromagnets. Sometimes you get part behaving this way, so and part behaving that way, and then in some sense we can say that they have a phase transition. Even this looked like a very small problem. This is a very difficult problem, since if we can solve this problem, then there are millions of applications in different areas. Let's look at how we can model this using a Markov random field. So the parameterization of this model, the potentials look like this. We are looking at a variable pairwise potentials here. Obviously, each of these variables can spin up or spin down. So plus 1 or minus 1. So here we write it as e to the power minus w, e to the power w, where w is a non-parameter which we have to compute or we have to assume. What is the energy here? So here the energy is minus w, right? The potentials we have seen was e to the power minus e, right? So here the energy is minus w. So if w is positive, then the system would like to go to low energy. Low energy means high probability, right? So which situation in this table is going to give low energy? Low energy means high probability. So which situation is going to give you low energy? So if w is positive, then energy is minus w. In which configuration are going to give you low energy? First one, both are positive. And then here plus minus, here is minus and plus, here is minus and minus. Then which one? Then which one will give you low energy? So either they have to be both positive or both negative, both spin up or both spin down, right? Then only I can say that it is uh, high probability or low energy. So we have seen that the normalization we do for in Markov random field is a headache. Why? Because in general, to compute the normalization factor, so for a small problem like this, also the normalization factor computation is NP hard. So even for Ising model, this computation of the normalization factor is NP hard. In a simple 2 by 2 Ising model itself, the computation is very, very hard. And then if the model is a big one, then it we, mo- we the partition function can be computing the partition function can be done in polynomial time for associative Markov network, but it is NP hard in general. The icing model you can generalize to a fully connected icing model. All the entries in W are pairwise potentials here. With this, what you get is known as a Hope field network. This was one of the early applications of probabilistic graphical models in 1970s, 80s, etc. Let's see this example. In this Hope field network, what you give is a lot of training images. So you train the system, you can learn all the parameters of the system, and then somehow you provide. The idea here is that to actually give this training image, to actually give this training images with what we do is we train the system, and with this. So the idea here is to actually give this training images with lot of black pixels, and then the Hope field network is trying to figure out what it corresponds in the training images. So this is an application with Hope field networks, and that's why it is called associative memory. Means that you have already memorized many images, and you want to make fast decisions using the incomplete version of the images which you're giving as input, and you try to figure out what actual images what is the actual image from the incomplete image. The method you use to solve this problem is iterations, which is using an algorithm called iterative conditional models. Iterative conditional modes are based on figuring out the most likely state of a node given all the other nodes. This is the model in terms of sigmoid function. Probability of y is equal to 1 given y minus s comma theta is a sigmoid function. So this model actually has an exact solution. So if you look at the icing model, if you want to find out the values of a pixel and all the neighboring pixels are +1, then the icing model will give you something like it also goes to +1, where in some sense that's what it does. You can see that how field network are very much related to recurrent neural networks, and Boltzmann machines are actually extensions of this Hope field network by simply introducing hidden variables in Hope field network. In addition to the things what we have seen here, you add hidden variables. Inference in such models often uses Gibbs sampling, which is a stochastic version of the iterative conditional modes, which we have seen just now. A third example is Potts model. This model is same as icing model, but you are allowed to use multiple discrete states. So in case of three discrete states, the tabular form of the potentials will look like this. This is a very important model in multiple areas. Here is an application of the pods model using different strength and trying to find the map estimate of the or the lowest energy of the system, you notice that when J is very big, you get clusters that are spin up. Where when J is small, you get small clusters. Obviously, for some value of J, there is a phase transition, right? And this is an important area or important question in which people do research. People actually try to find out what is the value in which the phase transition occurs, etc. So here you can think this being the actual pixel values, and can be discrete states, and the unobserved variables, and they are defined over a grid. So there is a good way to model this as a set of variables is through an undirected graphical model. So you have a grid of values here as an undirected graphical model. A very good way to describe this observation is by using a directed model. So these are the observations X, S, S, T, etc. So you have a mixture of the undirected model undirected and directed model. Undirected model is to model the correlation of grid variables, and to then describe the observations. You use a directed model, and this is the prior distribution of y, which is a Markov random field, and these are the potentials over edges, and these are the observations. The observations are defined using a directed graphical model.